Salme Cook. I'm a PhD candidate at the University of New Hampshire and a Blue Waters Fellow. Today I'll be talking about bed shear stress on estuary mudflats. So estuaries are these dynamic coastal environments where salty marine water mixes with fresh river water to create some of the most productive environments in the world. So the mixing in these environments is largely driven by tides, the atmosphere, waves, and rain events, and then seasonal river events. It's at these fronts where you have a trapping mechanism where sediment and nutrients settle out of the water, which is one of the reasons why it's such a productive environment. It's when you have excess nutrients and excess sediment in these environments where you start getting impaired water quality and water clarity, and leads to what we call eutrophication. So we think about the value of these systems in terms of their ecosystem services and their economic values. So some of their ecosystem services are this buffering capacity, or this ability to settle out nutrients and sediment in the system, which I talked about previously. It's important for the nitrogen and phosphorus cycling in these systems. There are also habitats. They're called nurseries of the sea, and in the United States, actually 75% of the commercially caught fish spend some portion of their life in estuaries. It's important for shore stabilization and flood regulation, estuaries are, that is, and it was found that after Superstorm Sandy, $625 million worth of damage was prevented because of things like wetlands and mudflats. They're also very important they're very high primary productive environments, and they're important for carbon sequestration, which is what we call blue carbon. Some of the economic values, it's no surprise that of the 32 largest cities in the world, 22 of them are located on estuaries. And in the United States, 14% of coastal communities produce 45% of the nation's GDP. 76% of trade involves some sort of marine transportation, and coastal recreation in these environments brings in $8 to $12 billion a year annually. So they're important environments to protect and understand. The biggest threat to the health and welfare of these environments is eutrophication, and that's induced by excess nutrients from increased human activity, and that's sort of the impaired water quality and clarity I was talking about. It's one of the most widespread, costly, and challenging environmental problems. All right, so the nutrient problem. We have a pretty good understanding of the point sources of nutrients, specifically nitrogen and phosphorus, into our water bodies from wastewater treatment plants, stormwater outfalls, and non-point sources, mainly transportation, industrial operations, agricultural operations, and from fertilizer and also animal waste. But there's a point source, or there's a source we've largely neglected, and that's within the estuary itself, and that's nutrients from sediment resuspension. So my research is motivated by this question: does sediment resuspension contribute to nutrient loading? So that's where bed shear stress comes into play. So this is how shear stress relates to that nutrient loading. When you have water, when you have a fluid interacting with a boundary, it applies a shear stress at that boundary. And in our case, we have our fluid are just the motions of the hydrodynamics over our system, and that induces a bed shear stress. When it exceeds some critical threshold, which is set by the sediment characteristics, the characteristics of the bed, when it exceeds that level, you have some sediment resuspension, and depending on your environment, you can then release nutrients into the water column. And those nutrients either can be within the pore waters or attached to the sediments themselves. For our particular site, which we'll talk about later, we need greater than 50% mud fraction, which is why we look at estuarine mudflats, and greater than 0.35 newtons per meter squared for nutrient release, and that was based on a lab study that was done in 2013. The challenge here is that you cannot measure shear stress directly. You have to measure the velocity gradient in the overlying water column. So what we're going to do is estimate that shear stress using modeled currents. So this is just a schematic of what a typical tidal boundary layer looks like and what a wave boundary layer looks like. For the purposes of this talk, I'm only focusing on the tides. I don't have enough time to include both. Plus waves is kind of some current research that we're doing. So you can see that shear stress is related. It's proportional to that velocity gradient. And in a tidal boundary layer, although it's not as strong as a wave boundary layer, so the shear stress here won't be as strong as here, tides last on the order of hours, whereas waves last on the order of seconds. And the environment I'm going to talk about is tidally dominant. So there's different ways you can estimate shear stress, either a quadratic drag law or a logarithmic law of the wall. We'll be using a logarithmic law of the wall. All right, so the study site that I look at is the Great Bay Estuary. It's located within the Gulf of Maine, which is one of the most productive environments for, at least for fisheries in the world. The Gulf, or the Great Bay, is one of what they call estuaries of national significance. It's within the EPA's National Estuary Program. As I said, it's tidally dominant. You have currents on the order of 1 to 2 meters per second, which is really fast for a coastal environment. And its tide range is on the order of 2 to 4 meters. So it's like 3 to 12 feet. It has relatively low river input. It's less than 2% of the tidal prism, despite the fact that it has 7 rivers that feed into it. And it has really deep tidal channels that have fringing mudflats here and here. And this is about 5 kilometers by 5 kilometers. And some of those fast tidal currents come in through this channel. But it's been showing signs of eutrophication. Of all those estuaries in the EPA's program, this is one of the most pristine, and it's started to show signs of eutrophication. So we're really interested in why that is. So the modeling system I use is COAWST. It's a coupled ocean atmospheric wave and sediment transport model. Since I'm only looking at the tides, I've only turned on the regional ocean modeling system, the ocean model in this case, which is a 3D free surface topography following numerical model. It solves the Reynolds average Navier-Stokes equation with finite differencing. The code is written in Fortran and uses some C pre-processing to activate different outputs that you choose. And the output data is written in NetCDF. So this is the model grid. I've made this in MATLAB. This visualization, I'm going to use a different program for the rest of the talk. It's gridded horizontally by 30 meters because that gives us some of the major features in the bay. We also have a 10-meter grid that we have running, but that's sort of some future work. It's gridded in 8 vertical levels, which are terrain following. The grid was developed using many different data sets. LIDAR, some bathymetry data we collected ourselves, and other data from the Army Corps of Engineers, NOAA, FEMA, and the USGS. So without some of that publicly funded data, we wouldn't have this bathymetric grid. And the gridding routines were done in MATLAB to create a NetCDF file, and that's one of the inputs into the model. So this is the other, this is sort of the visualized grid that I'm going to be using for some of the visualizations I'll talk about. And this is actually, I used a DEM for the areas that I don't have. You can see I don't have data here, but for Viz, it just looks more pleasing if you have data in these holes. So green indicates areas above mean sea level, and brown indicates areas below mean sea level. And this was done using ParaView. So, and this is a zoom in of the Great Bay. So these are where the mudflats are. So I'm eventually going to show a distribution of shear stress that's estimated and then a nutrient load from a tidal signal. So you can see that the tidal channel here is about 15 meters deep, and then the rest of the bay is on the order of 3 meters on average. So it's a pretty shallow environment, which is difficult numerically to implement. So this is the model configuration. My time steps, 1 to 1.5 seconds. My horizontal resolution is 22 kilometers by 25 kilometers, gridded into 30 meters, is 700 by 800 cells relatively. 8 vertical levels. It's run for 30 days because if you're looking at this tidal signal, it's modulated on a 30-day sort of time. So that's really what takes the bulk of our time on blue waters, is these long runs that we need. So what we've done is we've run 4 different cases for both tides and including subtidal, which corresponds to meteorological forcing. And what this sort of parameter does is it fits into this drag coefficient, which then gets put into this estimate for shear stress. And I'll show that in a little bit more detail later. So essentially, we look at a tide gauge for our forcing in this model. And these are observations over 45 days. If you filter out the data for those atmospheric conditions, you can see there's not a lot of atmospheric forcing here. But regardless, we ran models just to prove that point. And then the bottom is just what our tidal forcing file actually looks like. So just a couple weeks ago, I submitted a paper that was using data from blue waters, and we found that 0.02 was sort of the best bottom roughness, although this model isn't that sensitive to these bottom characteristics. And we found that subtidal observations were not that important, which for the next step, if we're going to look at shear stress, we really want to have a validated model. So that was our first step. This is how the model estimates shear stress. If you include sediment transport, you can have different layers of sediment. We don't. We just have vertical levels or vertical layers of water overlying a bed. Now, if you take that lowest cell and you sort of zoom in on it, the velocities are shown at those mid-cell levels for U and V, and then based on what you decide you want your bottom boundary condition to be, either that quadratic or logarithmic law of the wall, you fit that to that bottom, and then you have a prescribed bottom boundary condition. So here, the output of the model is tau b in the x direction and tau b in the y direction, with those u's coming from the model and the z naught from something you prescribe. So I think for us, we're pretty lucky because we can also go out and collect observations of shear stress, and this is how, well, observations of velocities and then estimate shear stress from that. So this was work that was done by a master's student. She just defended a couple weeks ago. And she went out and deployed instruments in 3 different locations, but there's a lot of eelgrass here, so she didn't get very good data. And B had the strongest currents so that she could actually make an estimate. So what she did was she deployed an instrument. You can see it's exposed at low tide, so that's what these gaps in the data are. And I want you to focus, so I guess I should say the top plot is her tidal signal, and then the directional component of the velocity, and then the velocity magnitude. So if you focus on the flood tide and the ebb tide, you can see that the flood tide's about 25 centimeters per second, but also pretty short, and that the ebb tide is about 15 centimeters per second, also, which is much longer than the flood. She uses the same law of the wall formulation, and she had 2 preliminary estimates of shear stress. She found that on the flood tide, you could see about 0.41 newtons per meter squared of stress induced by the flow. She averaged it over that entire tidal cycle. And then for the ebb, she found 0.23 newtons per meter squared. Now you can imagine if we're using that lab study that found that 0.35 newtons per meter squared actually fluxed nutrients into the water column, that it's only on flood tides that you would get nutrients, but from this particular location. So the problem we found was that, great, we have these estimates, it's only for one location in the bay. So how can you extrapolate that to the entire estuary? You can't. You really need a numerical model to do that. And these estimates came from a 3-year master's degree, so models come much faster than that. So this is a video in pair view of the tidal signal from data that we collected using blue waters. You can see that as the tide comes in, those are those darker colors, it fills the entire estuary, and then you have draining on the ocean before you have draining in the bay. There's about a 2.5-hour time lag between tides, high tide in the ocean and high tide in the bay. You can see at low tide those sort of wetting and drying. The model is getting that, which has been a numerical issue in a lot of other ocean models. And it was only implemented in 2013. So first we look at that tidal signal, similar to that first graph that Kara showed. Now I'm going to show you a movie of the velocity, direction, and magnitude. So this, I'm going to have to, all right. And the bottom is just the tide, just to show you, there we go. All right, so you can see that during ebbing tide, the arrows are pointing out, and then the tide switches and comes back in. The red time series corresponds to a point in the channel, and the blue time series corresponds to sort of a random point on the mudflat, just to show the difference in current velocities from the channel versus the mudflat. Now we care about areas where there is mud, and our mud fraction greater than 50%. And I can tell you that the channels are mainly bedrock and rock because the currents are so strong, they would pick up anything that's fine and just carry it out of the system. So we are eventually only going to look at areas where there is mud. And sort of this last idea, or the last thing I want to show you is a video of shear stress. Again, noting that 0.41 was just a value from flood tide, 0.23 is from ebb tide, and then the estimates for nutrient release was 0.35. So The dark red colors are 0.5 newtons per meter squared. So mudflats are generally sort of these shallow areas, and you can see that at our particular location, at every single tide, it's greater than 0.35 newtons per meter squared. So you would expect that there'd be nutrient release, at least in these areas, during all portions of the tide. And I should say that CARA's estimates came from a location out here, which is why they're a bit smaller. But again, that's only one location on the bay, and now we've got estimates everywhere within the estuary. So if I make an estimate, and then I can make an estimate of nutrient release from a tidal cycle, which was what we were trying, our goal in the first place. So this shows how we ramp up the model from rest, and I'm only going to use data from 2 to 7 days. I've run a 30-day run, but this is 2 to 7 days. Again, using a channel and a mudflat, you can see that the channel is much stronger, but the mudflat's what we care about. And anytime you see these sort of fuzzy crosses, that's above that 0.35 threshold. If you use a model for mud fraction in the entire bay, greater than 50%, areas with greater than 0.35 newtons per meter squared shear stress, you can calculate a nutrient load. And that's what this pink and green lines are showing, that on every tide you have flux of nitrogen and phosphorus into the overlying water column just from the tides. How does that compare to, let's say, river load or loads from an event? So rivers are pretty seasonal, and I found that on one tidal cycle on average you have about 96 kilograms of dissolved inorganic nitrogen and 34 kilograms of phosphorus. There's an asterisk here because that study didn't include uptake, so there's some chemistry there that I don't quite understand, but that's a preliminary value. So then if you take that and account for a month, you can see that it's on the order importance of a river. So in conclusion, it should be this should be a load that we should care about when we're making nutrient load estimates to estuaries. So in summary, our research goal is to estimate the distribution of shear stress across the bay. Our conclusion after we made that estimate was that we found that sediment resuspension could be a potentially significant source of nutrient release and should be considered. We used a verified numerical model, which has been the subject of a paper I submitted a couple weeks ago, and that was verifying it for tides. Now we can go on to this shear stress question, and we estimated that shear stress based on observational estimates of shear stress. We really need more observations to validate this model for shear stress. And sort of a sneak peek, I'm going to look at how horizontal grid resolution affects our estimates of shear stress. This was just a graph I showed from a talk I gave at Ocean Sciences in February showing tidal signal, velocity magnitude, and shear stress estimates based on a 30-meter, 10-meter, and 2-meter grid. You can see that they're a little different, and if you care about 0.35, that might matter if you're looking at resolution. So that's something that I'm working on in the future. And also incorporating waves, as I sort of talked about in the beginning, and sediment transport. This is the distribution of sediment based on observations in our estuary. This is a modeled sediment suspension event, and this is how we're going to collect observations on about waves. And I'd like to thank everyone that helped in this research.